All right. Welcome everyone to a short little video on a practice problem dealing with forces for Physics 1. I'm going to explain to you what this practice problem is in words, and then I'm going to draw the picture and kind of walk you through every step on how to solve a problem. And this is just about forces. I'll do another video on different topics later. So this practice problem that we're going to do today is as follows. We have a ball being pushed up a hill by some applied force. It could be a person, it could be a string. We don't know, we don't care. There's just an applied force on a ball that's being pushed up a hill. And our hill, I was going to use black. Hold on. This is the wrong. Okay. So our hill happens to be 30 degrees above the horizontal. That's the incline of our hill. And our ball sits on top, right there. It's a weird color. And I didn't draw it, I'll draw it a little better. So our ball is on the hill, right? And it's being, it's being pushed this way with an acceleration of 2 meters per second squared. All right. And we want to find the force required to push this ball up the hill at this acceleration. And we're going to assume the mass of the ball is, let's say, 50 kilograms. Okay, and we're going to do this problem twice. The first time we're going to do it without friction. We're going to neglect friction on this hill. And the second time we're going to do it with friction, just so you guys can see how they relate. So let's say the coefficient of friction, I'll give us 2. Let's say this one is 0.1 and this one is 0.15. And those are unitless numbers. They're just a coefficient, like a scalar quantity. So let's say part A, we'll do part A first. So the first thing we're going to do is neglect friction. Friction. Okay. So the first thing we want to do in any force problem is we want to draw our picture. Really, the first thing we want to do for any physics problem is draw our picture. And we have our base picture here, this thing. That is our base picture. But we want to also include our forces and everything now. That's called a free body diagram. So the first thing we're going to do is draw all of the forces acting on it. So this is the force due to gravity. This is the normal force because it's on a surface. The normal force doesn't exist if your ball or your object is hanging. So like a short little tangent here, if our ball was hanging and this was a rope, there is no normal force because it's not on a surface. So you can kind of think of the normal force as a reactionary force that is keeping an object from falling through or going through another object. So like the normal force kind of exists in that if you lean against a wall, you're not going to fall through the wall because there's a normal force keeping you from doing that. And breaking through a wall would be your applied force is bigger than your normal force, but that's way down the road. That's like engineering stuff. And it may be some higher physics. And then we have one more force over here like this. And this is our applied force. And that's what we're looking for. So the first thing we're going to want to do is make our coordinates axis and break our forces into components. Now a trick for inclined plane problems is to, there's an erase button on my stylus and I keep pushing it on accident. We're going to tilt our coordinate system so that our x-axis is along the incline. And the reason we're doing that is because now the normal force here and our applied force here, now the two of them exist in one direction at a time, which is what we need for forces. Because just like with kinematics, you have to break your forces into x and y components and then solve the different directions separately. And there are ways to tie them into each other, which we'll see when we get to the include friction, but for now, just The two of them are exclusive, mutually exclusive. And that's important because right here, I'll come back. So, stop. Touchscreens, man. So right here, this now is the force component of f of g. Because I don't know if I can rotate it, but like if you just kind of visualize, this right here, this line that I've drawn, is now strictly in the y direction, and this one's in the x direction. Even though they are tilted, according to our coordinate system, that is true. And that's great because that means we only had to break the force of gravity into x and y components instead of the normal force and the applied force, which we would have had to do if we didn't tilt our axis. And I mean, you could still do the math like that, it would just be a little more difficult and there's more chance for error that way. And one more thing that we can just assume from the problem is that this angle right here, this is 30 degrees as well, due to similar triangles. Where this is a right angle and this right here is a right angle, so you can kind of picture this, if this triangle here was rotated and flipped, it would be the same angle, right? You can kind of see that? And now that we've assessed that, we're going to want to find the x and y components of our force of gravity. So FGY there's also a formula for gravity, and that is mass times acceleration due to gravity. Not all forces have a formula. Gravity just happens to be one that does. So like normal force up here doesn't have a formula, and tension doesn't have a formula. Friction has a formula. And our applied force kind of has a formula. It's in a general sense, what is that? That's work. So the applied force doesn't really have a formula. It's just some Newton that's, being introduced to our system here. But enough about that, we're back on our force of gravity in the y direction, our y component. And since we have to break this into a component, this is our original force, and this is the y component, and this angle is 30 degrees. So according to SOHCAHTOA, or trigonometry, we can use cosine of 30 to find this component, and that would be with the law of sines, right? Or we could just do, right? So cosine is the adjacent over the hypotenuse, so cosine of 30 is the adjacent, which is y, divided by the hypotenuse, which is mg, which is what this is. So if we want to get y by itself, we just multiply mg to the other side, and we get mg cosine of 30, which is this over here. And since the y direction is cosine of 30, the x direction has to be sine. It's one or the other. This is sine, not cosine. Sine of 30, one or the other. And now we have all of our forces. So this guy right here, some unknown value, that's what we're solving for. This guy right here, another unknown value that we can't plug into a formula like we do with gravity. That's fine. So we're going to do this formula right here. And we're going to use that as our basis for our math. I'm going to rewrite that up in the corner so I have some more room. Okay, and this right here, actually, like I was saying before, it's in one direction at a time. And these y's are different values. So this y right here, or not this y, this a, sorry. So this a right here is the a in the x direction because it's following the x-axis. And there is actually no a in the y direction because in the y direction, our ball is not, flying off the ramp, nor is it going into the ramp. So it's kind of being held in that plane, which makes our math a little easier. And I'm going to go ahead and do I guess we'll do the x direction first. Okay? and I'll explain why in a second. So our 50 times our 2, oops, no, 2. So that's our 50 kilograms times our 2 meters per second squared equals all of the forces in the x direction. So we have our positive applied force, and we know it's positive because of which way the arrow is pointing in our picture, minus the x component of the force of gravity, because we know that way is going down the hill. And I figured out those directions based on the tip to tail method, if you remember back to how to add forces together. So it's going down and it's going to the left, and that's why the x and y components are oriented as such. And we found with our math, or with our trig, that the x component of the force of gravity is mg sine of 30. So if we want to get F by itself, F equals 100, so 50 times 2, plus 50 times 9.81, when that's the mg, times sine of 30. And I will find out that math real quick. 100 plus 50 times 9.81 times sine of 30. And we get 345.25, I'm just going to leave it at 345 newtons. And that is our answer for the force required to push this block, or this ball, up a hill if we neglect friction. And you'll notice that I didn't bother with the y direction for this, and that's because the formula for the force of friction is the coefficient of friction multiplied by the normal force. And the normal force we have to get using the y calculation, and that's kind of how the x and y directions relate to each other. But since we're not including friction, there's nothing in our math that relates what we're solving for to the y direction, so I didn't even bother doing the math for it. But we're going to do it now, since we're going to include friction. So I'm just going to erase some stuff. I'll leave it for a few seconds so you guys can kind of see my methodology here. And I also neglected to put units in my actual calculations down here. I would recommend doing that, like on tests and stuff, just because I remember when I took the class, it was a huge impact on partial credit and everything. I just don't when I'm doing the math because I'm out of the habit and I don't need to do that in my current classes. But now I'm going to erase all of this. Most of the stuff is going to stay the same, so I'm going to erase this, and now we're going to include friction. Okay, and we have two coefficients of friction here, right? We have the coefficient of kinetic friction and the coefficient of static friction. That's what the K and the S stand for. So now we have one more force right there, the force of friction. Being pushed, it's always going to resist movement, so since our ball is going up the hill, our force of friction is going to make it not want to go up the hill, if that makes sense. And we have our formula up here at the top, where this is the coefficient is the main part of this formula, the coefficient and the normal force, of course. But as you can see, we have two coefficients, and that's because when something is moving, it is easier to keep it moving than if you were to make something start moving. So there's a bigger frictional barrier, I guess, that the force has to overcome to make an object start moving. And that's why the static friction is larger than the kinetic one. And you might be given both, like on a practice question or in life or whatever, and it's up to you to decide which coefficient to use. In our problem, we know that this ball is rolling, and it has this acceleration, which means we know that it can't be the static friction, because this ball is rolling, which means kinetic. So this is our component, or this is our coefficient that goes in here. And now that we've kind of puzzled that out, I'm going to rewrite this. So this is 0.1 n. Okay? Now that we've kind of puzzled that out, we're going to redo our math to include friction. And this time I'm going to start with the x direction once again. And our mass is still 500 and our acceleration is still 2. And we still have our positive applied force. And we have our negative gravity, x component of gravity. So 50 times 9.81 times sine of 30. And we also have our negative force of friction, so minus F of F, which we know, so I'm going to go ahead and write in the formula here. We know that is 0.1 n. That's what we found up here. And oh dear, we have 2 variables in our formula, which is no good. So we're going to have to figure out what one of these is. And our end goal is to find what F is, right? So the only one that we could maybe find is this guy right here. Luckily we can, using some of the forces in the y direction. And if you remember before, I was talking about how the acceleration in the y direction is different from the acceleration in the x direction. And in this case, our y direction acceleration is 0 because our ball is staying on the surface. It's not falling through the table or the incline, nor is it flying off into space. So the sum of our forces equal ma, but our a is 0, so that just means all of these equal 0, right? Because anything multiplied by 0 is 0. Which is going to make our math a little easier. And we're going to do kind of the same thing we did up here, where our y direction forces, we're going to sum them up, right? So we have positive n up here, and we have the negative, we have minus the y component of gravity. So 50 times 9.81 times cosine of 30. So we can rewrite this so that n equals 50 times 9.81 times cosine of 30, which is great, because now we can plug that in up here. You kind of see that? And I'm going to, I'm running out of room here. We'll make do. So I'm gonna change, we'll change back to green. So this is, I'm now gonna do this down here. So this is 100. 100 equals F minus 59.81 times sine of 30. I'm just gonna find that number. 245.25. Okay, and then we also have this minus 0.1 times this number, which I'll find as well, just so we have our formulas a little simpler. I find it easier to work with numbers instead of variables, and that's really up to you. So when you're doing a problem like this, in the homework or just, to practice, you don't have to find the numbers and then solve for the variables. You can leave everything in variable form and then plug in numbers at the end. That's up to you. I just prefer it the other way. So 424.8. 779. So 424.79. Okay, cool. And now we can just, add both of these to the other side and get what the force equals. So I'm going to do that, and the F is going to equal, so that's 100, right, plus 245.25, which is that, plus 0.1 multiplied by 424.79. And that equals 388 newtons. It's actually 387.7. I'm just going to round up to the nearest whole newton. And again, on homeworks or, just in life, it's probably, you should probably ask what your rounding what you want to round to. Normally you kind of follow sig figs. I just, for the sake of ease, I'm just rounding to the nearest whole number. And that's kind of, that's it. That's really it. I did this problem, the ball is being pushed up a hill, and I found the 2 forces required. The one without friction was less. It was 345 instead of 388. And that's because friction is obviously going to kind of take away some of the force. So you're going to need more force to move the same block the same distance. And you could do a similar problem like this. You can kind of like change the variables around. So maybe instead of we refine the applied force for part B when we include friction, we use the same applied force, and then we want to find what the new A is, or something like that. You know, it's just, that's kind of how all these forces play together. And you could have a problem that's more complicated, but this is kind of like almost every force is at play here. All the forces that you care about in Physics 1 anyway. I hope that helped you guys some, and I hope you guys have a good day.